In this video, we are going to do some additional work with infinite series. In particular, we want to expand on the theme of adding more terms to get a better and better approximation, number one. And number two, deal with operations on series. In other words, if you have a base or a library of series, you can actually get a lot of mileage out of that by manipulating those series to get new series. So let's go over to the document camera first and check out an example right here. Okay, so in our beginning example, we're going to write the Maclaurin series for f of x equals 1 over 1 plus x. Now, of course, we know how negative exponents work, so 1 over 1 plus x is equal to 1 plus x power minus 1, and that is very useful for taking the derivatives. And of course, the Maclaurin series is centered at x equals 0. All right, so we know that we are going to need the derivatives for our coefficients. So f prime of x, well, negative 1 comes down, new exponent is 1 less, so negative 1 times 1 plus x power negative 2. And of course we have to evaluate these at 0 to actually get the coefficient of the various powers of x. So if we plug in 0 for x, well, this just becomes 1 to the negative 2, and of course 1 to any power is 1, so this is really what matters. Very similar thing down here. If I differentiate what I've got up here, well, the negative 1 is just a constant multiple, so just comes along for the ride, exponent comes down, so we have negative 1 times negative 2 as our coefficient, new exponent negative 3. And we'd get that. I was kind of halfway through differentiating this, so we're taking the third derivative, exponent comes down, new exponent is 1 less, so the third derivative evaluated at 0 is actually, well, negative 3 times negative 2 times negative 1. I'm almost thinking of it like this. It's negative 1 to the 3 times 3 factorial, kind of in the way there. Okay, so the pattern I want you to see is we're starting with this negative 1 here. So every derivative we take, the new exponent is going to be 1 less. So we start with an exponent of negative 1, new exponent is negative 2. Differentiate again, now negative 3, negative 4. Okay, and every time we differentiate, we're also going to get one additional factor here out in front. So, in general, the nth derivative evaluated at 0 is going to be negative 1 to the n, okay, because all these coefficients out here are going to be negative. So you're going to have a bunch of minus signs. Sometimes they'll all cancel out, like right here, when we did the second derivative, negative 1 times negative 2, that's actually positive 2. Right? But down here, you get 1 left over. So the parity, in other words, the evenness or oddness of n will determine whether this is positive or negative. So this is negative 1 to the n, and then you'd have an n factorial. Okay, so when we write down the Maclaurin series, which of course says that f of x is equal to this, n equals 0 to infinity, the nth derivative evaluated at 0, x to the n over n factorial. Okay, well, we just got a formulation for what this is. It involves n factorial. So this term is going to cancel out the n factorial that we have in the denominator from the definition of our Maclaurin series. And what we get is this. We get n equals 0 to infinity, negative 1 to the n, x to the n. Okay, now of course, we know what a 0 exponent looks like. Anything to the 0 is 1. So you'd have 1. When n equals 1, this would be negative 1 to the first, x to the first. So 1 minus x plus x squared minus x cubed plus, and we would keep on going like that forever. Okay, let the ink dry there a second. You'll be able to see it a little more clearly. Okay, so this is an alternating series of the various powers of x. So very nice. So that'll be our base here. In fact, let me use a different color marker. It might show up a little better. And this is just so I have it. So yeah, thus 1 over 1 plus x equals 1 minus x plus x squared minus x cubed plus dot dot dot. Okay, we continue in that way forever. Now I want to switch over to GeoGebra just one sec here. Let me make that window nice and big. Okay, that kind of screws up what I did with the zooming in and making everything nice. Okay, I want to change my settings on this a little bit. I want my, okay, yeah, why aren't you actually doing that? I want my x min to be negative 2. I want my x max to be 2. Okay. All right. So this here in the green is a graph of f of x equals 1 over 1 plus x. All right. So tell you what, I'm going to put in a slider. And I'll put it over here, kind of out of the way, but okay, I want it to be an integer. That's fine. Okay, and then over here, we're going to use GeoGebra to write out the Taylor polynomial for our function f. We'll center it at 0. Okay, remember the Taylor polynomial is a little more general than a Maclaurin polynomial. Same thing with series. Taylor series, a little more general than a Maclaurin series. Taylor polynomial or Taylor series can be centered anywhere. When we're doing a Maclaurin series, it's centered at 0. Okay, and the order is going to be n, right? That's the whole point of having the slider. Okay, so as we increase n, we'll see this here. Okay, great. Now notice the calculator pane right here is not doing the canceling that we did before. If we switch back, you can see, okay, we said that the series should have been 1 minus x plus x squared minus x cubed. The coefficients were all either plus or minus 1, and it was alternating. Let's look back here. We can see, okay, we got a 1 minus x. It doesn't say plus x squared. It says plus 2x squared over 2 factorial. Of course, we know those cancel out. Same thing right here. 3 factorial, that's 6. It cancels out. Same thing right here. Okay, so it really is there. Okay, the thing I actually wanted to examine here is right here. You notice I've got these dotted lines at x equals 1 and x equals negative 1. Notice that the series, or the polynomial, as n increases, the polynomial looks great between those bounds. But once we leave those bounds, it starts to get weird. In particular, notice we're going way up there. It's never going to get down and touch this other piece, no matter what we do. And notice what's happening over here, right? As soon as we start to get near x equals 1, this thing just goes away. Okay? So the radius of convergence for this series is 1. And the interval of convergence is x values strictly between -1 and +1. Okay. If you review your calculus, you can check out your calculus book and find a test that will tell you what the radius of convergence is. Okay, so, or how to find the radius of convergence. But I did want to talk about manipulating series in this, doing operations on series. Okay, so let's look at this next example here. We're going to find another series. So let's find the Maclaurin series for ln 1 plus x. Okay. Now, you know you're starting to think like a mathematician when you try to build on the work that you've already done. So the work that we've already done is right up here. We have found from scratch, we did the derivatives, found the Maclaurin series for 1 over 1 plus x. Okay, now the thing that we're going to do here is we are going to note that if I were to integrate 1 over 1 plus x dx, I get ln of 1 plus x. Okay, actually there's a plus c there, but don't worry about that for right now. Okay, so I know the series for 1 over 1 plus x. It's right up here. It's a power series. Okay, and powers of x, that's the easiest thing there is to integrate, right? The first rule for integration that you learn in calculus is the power rule. Okay, so what I'm going to do is I'm going to integrate term by term here. So the antiderivative of this should have a series that's equal to the antiderivative of this series. Kind of makes sense. So integrate that, you get an x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4 plus dot dot dot. We would keep alternating like that forever. So we see that ln of 1 plus x should have this Maclaurin series expansion, ln 1 plus x, since this antiderivative is equal to ln 1 plus x. This should be our series right here. All right. Let's go ahead and check back with Geogebra and see how that looks. Right? We can check and see if it's reasonable. Okay, so we're back looking at Geogebra. I'm going to go ahead and change f of x. Okay, I'm going to make it ln of 1 plus x. Okay, so we can see in the green here that we have got that natural log curve. Now, if I kind of change my settings again, let me go and let's make the y max like 3 or something like that. It'll be a little bit more familiar picture. Let me move this slider out of the way. It shouldn't, we don't want it up there right now. Let's put it over here. Okay, so in the green you can see ln x. Okay, so the blue is the Taylor polynomial. Okay, so first degree Taylor polynomial is x. Okay, now over here we've got, or sorry, Maclaurin polynomial. But a Maclaurin polynomial is a Taylor polynomial centered at 0. Okay, notice the first term, x. Let's see, is the next term going to be negative x squared over 2? Let's go and check it out. Oh, okay, negative x squared over 2. Okay, let's do some more. I'm supposed to get plus x cubed over 3. All right, now, certainly doesn't look like x cubed over 3, but if we think about it a sec, 3 factorial is 3 times 2 times 1, and then I've got a 2 out in front here. That 2 would cancel out with the 2 and the 1 down here in the denominator, so I get x cubed over 3, and x to the 4th over 4, right? Same thing down here. 5 factorial is 5 times 4 times 3 times 2 times 1, and 24 is 4 times 3 times 2 times 1, right? 4 factorial is 21, so this is really 4 factorial over 5 factorial. So the 4, 3, 2, and 1 will cancel, leaving you with just a 5 in the denominator. So we really are getting the series that we found by integrating the series for 1 over 1 plus x. Okay, so if we look here, we see kind of the same business that we were seeing before. Okay, notice after we pass x equals 1, this thing just shoots away and is nowhere near the curve y equals ln 1 plus x anymore. So we really do need to stay between negative 1 and 1 in this case. Now, I think we actually do luck out with this new function, and I think positive 1 is actually part of the interval of convergence now. Okay? So we could do a little approximation here. Let's try something fun. We'll talk about approximating ln2. All right, well, in this series we can see, okay, if I plug in x equals 1, the left-hand side will be ln2. And the right-hand side would be 1 minus 1/2 plus 1/3 minus 1/4, and it would keep on going like that. Okay? The more terms we take, the more accurate the approximation will be. And we can write a program later on in the course. We'll show how to write a very easy program in Python to get the first couple of decimal places if we want. Okay, but one of the purposes of using these series is to help us get approximations for things that we can't kind of get analytically. And I know the value of ln for a couple of specific inputs, like ln1 is 0. I know that. ln1 is e. Is it? No, sorry. Whoops. ln of e is 1. Got that backwards. ln of e squared is 2, etc., etc. But ln for any other value, I can't really tell you. But I can get an approximation, and I could do it using this series as long as we stay in the radius of convergence for my series. Okay? So the moral of the story is if you have certain Maclaurin series in your repertoire, you can manipulate those and get new ones without going from scratch every single time. If you want to do something like integrate, Okay, if you know the series for your function and you want the series for the derivative, well, differentiate both sides. If you know the series for your function like we did right here, and you want the series for the integral, well, integrate the series. Okay, now, there are some subtleties that we're sweeping under the rug, and in your advanced calculus class, you can talk about how we can be sure our manipulations actually give us the right answer, because we do have infinite processes, and you've always got to be a little careful. But that's the basic idea.